Okay, so good afternoon everyone. Let's continue the proof of theorem 4.20, 420, nice number. Sounds better in Hindi, 420. Anyways, so okay, so we are trying to prove the subadditivity of the B function across separating cuts, right? So if you have a matching chord graph G and a separating cut C, and G1 and G2 are the C contractions, we want to prove that B of G is less than equal to B of G1 plus B of G2, right? And equality holds if and only if C is a tight cut. Yeah. So quick recap of what we already discussed. We are proving by induction on order. If the cut is tight, well, equality holds, nothing to prove. So therefore, we may now suppose that the cut is not tight. Well, you have a separating cut that is not tight. That means the graph is not bipartite, which is equivalent to saying that number of bricks is at least 1. And in fact, we know something more. Each shore induces a non-bipartite subgraph. Because if any shore induces a bipartite subgraph in a separating cut, then it is actually a special barrier cut and a tight cut. So therefore, because each shore induces a non-bipartite subgraph, we can conclude that both the contractions are non-bipartite, and therefore they have at least 1 brick each. And if the number of bricks is 1, well, then you are done. 1 is less than 2, inequality holds, strict inequality. So now let's suppose that number of bricks is at least 2. So the graph is neither bipartite nor a brick. Therefore, it has a non-trivial tight cut. Yeah. Okay, well, in particular, it's not a brace, not a brick, right? Can't be a brace because it is not even bipartite. So there's a non-trivial tight cut. Let's take any non-trivial tight cut, D. So now we have 2 non-trivial cuts. C is of course non-trivial because it is a separating cut that is not tight, so it can't be trivial, right? Observe that the statement never said it is non-trivial. Of course, the statement holds for trivial cuts. They are tight, right? So we have 2 non-trivial cuts, C and D. One of them is separating but not tight. The other one is tight. And we will consider 2 cases. Either the 2 cuts are laminar or they are not crossing, or they are crossing. So let's make a drawing. It's going to be a bit challenging, but let's see. Let me make the drawing here, or let me draw the graph G here. Okay, this is my graph G. We have 2 cuts, blue and pink. I don't know what convention I used yesterday. Mostly blue was the horizontal cut. C, X, X bar, and oh, this is the laminar case. So I'll draw both of them vertical. Looks nicer to me at least. Okay. So my graph G, I have the primary cut C, X and X bar, and I have the other cut D, and if I'm not mistaken, I followed this convention. No, Y bar and Y. So in particular, this is odd. This is odd, and this is a set X bar intersection Y. This is even. Yeah. So what we'll do is we'll consider the 2 C contractions, and we'll also consider the 2 D contractions and see what we can do from there. So I'll draw them here, the C contractions. This is my set X, and this is the vertex X bar. This is our graph G1. Yeah. And let's draw the other C contraction. This is my set x bar. This is little x. This is G2. Yeah. And this cut D continues to exist here. It is a cut here. Right? I'm not making any more claims about it. And this side is y bar. And the other side is x bar intersection y along with little x. That is the other shore. Yeah. So these are our two graphs, G1 and G2. Okay. And while we are at it, let's also finish making the other drawings. So let's draw the D contractions. So the first D contraction I'll draw is I'll keep this as it is and I will shrink this. So this is going to be my little y bar. Okay. And this is the set y. This is my graph H1. And well, I'll also draw this cut, why not? This is my cut C. And this part here is x bar intersection y. Yeah. Okay. Maybe I'll not label this, I'll just put x over here. Yeah, this is fine. This is H1. And now let's also draw H2. So this sliver will remain. This is my set y bar. And all of y, which is this big set, has been shrunken into a single vertex. Right? And this is H2. All good? Yeah? Okay. Now because D is a tight cut, we can say something nice over there. Right? Since D is tight, maybe I'll use some spaces here. I may want to make more drawings here. That may not pollute this part. We know that number of bricks in G is equal to number of bricks in H1 plus the number of bricks in H2. Great. What we want to prove is number of bricks in G is strictly less than number of bricks in G1 plus the number of bricks in G2. This is the goal. Right, so somehow we want to go from here to here. So it would be nice if you could somehow relate H1 and H2 to G1 and G2. And the first thing you note is that if you consider the C contractions, of course we have not argued that C is a separating cut, but if you consider the C contractions of H1, one of those graphs will be exactly G1. Is that something you all agree with? Whether I shrink a subset and I then shrink the bigger set containing that subset, or I directly shrink the big set, those are the same things. Yeah? Yeah? So one of the contractions, yeah, so let's also draw the, maybe. Let's draw the C contractions of H1. Okay, so in one of them I'll keep this x as it is and I will get little x bar. Let me call this H11 for now. Yeah, and the other one I will keep this sliver as it is and I will shrink the other thing, and this is going to be my H12. These are the C-contractions of H1. Okay. What is this set? Oh, by the way, this is fine, right? Yeah, this is y bar. Yeah. So this is my x and this is oh wait, I think I made a mistake. Yeah. I wanted to keep that vertex. Little y bar. Yeah, I'm going to keep all of this as it is and I'm going to shrink this part. So this is x bar intersection y. Okay, this is the graph H12. Yeah. Okay. Of course, one issue is we haven't argued that C is a separating cut. One of these graphs, of course, is this graph. So this is matching covered, but we don't know whether this is matching covered. But that's not the best way to go about things. The better way to go about things is to use a characterization of separating cuts. For every edge, can you find a perfect matching that contains that edge and meets the cut in exactly one edge? Right? So we are asking this question for H1. In H1, if you take any edge, then can you see or prove that there is a perfect matching containing that edge that meets the cut C in exactly one edge? Well, that edge, whatever that edge is, it exists here. Every edge in a smaller graph has an image in a bigger graph, right, in the corresponding bigger graph. So therefore, this fellow, this edge, whatever you pick here, exists here. And here this is a separating cut. Therefore, here there is a perfect matching that contains that edge and meets the blue cut in exactly one edge. Well, the pink one is a tight cut, therefore it will necessarily meet it in exactly one edge. Take the restriction here, that is your perfect matching. Yeah. So therefore, this is indeed a separating cut. Okay. Note that C is a separating cut in which graph? H1. Therefore, by the induction hypothesis, we can say that the number of bricks in H1 is less than equal to the number of bricks in H11 plus the number of bricks in H12. Yeah? Everybody agrees? This much we can say for sure. Yeah, because it is a separating cut. Okay, I'm not writing everywhere by induction hypothesis, right? I will use the induction hypothesis in many places. I will not write it, but in general you should write it. Okay. But can we make it stronger? If we know that it is a separating cut that is not tight, then by the induction hypothesis we can make it stronger. So is that true? Is it true that C is a non-tight cut? It is separating, we know. Can we also argue that it is not tight, or can we not argue? I don't know. Let's see. We know that C is not tight here. In the original graph, C is not a tight cut. Right? We assume that, otherwise we were done in the proof. So therefore, in the original graph, there is a perfect matching that meets the cut C in 3 or more edges. And I can always say 3 because odd number, yeah. So there is a perfect matching in the original graph that meets the cut C in 3 or more edges. Well, but the cut D is again tight, right? So therefore it will meet the cut D in only one edge. Now the restriction is again a perfect matching of the graph H1 that meets the cut C in 3 or more edges. Yeah. So therefore we can also say that it is not tight. So therefore by the induction hypothesis, we have a strict inequality. Yeah. Because we want to establish a strict inequality in the end. So somewhere you better get a strict inequality. Right? Our original one is just an equation. That's not going to help you. Somewhere you need a strict inequality in order to prove a strict inequality. Right? So that's this step here. Okay, good. Good. So what does that mean? That means that if I combine these two, then the number of bricks in G, which is equal to this plus this, therefore it is strictly less than number of bricks in H11 plus number of bricks in H12 plus number of bricks in H2. Yeah? Combining those two, we get this. But we have observed that H11 is simply the graph G1. Yeah? H11 is exactly the graph G1. So, I might as well write number of bricks in G1 because I want G1 on the right hand side plus number of bricks in H12 plus number of bricks in H2. So we are getting closer. We have gotten G1 on the right hand side somehow, right? But we want G2 instead of this creature. Yeah. So what is that? H12, number of bricks in H12 and number of bricks in H2. What's going on here? Do you all see how this is related to this? Right? In particular, if I were to draw the D-contractions of this graph, I would get exactly this graph and this graph. Let's just draw it. Why be lazy? So let's just draw it. So what are the D-contractions? In one case I will keep x bar intersection y as it is. I will keep little x as it is. And I will shrink this fellow into little x bar. Is that okay? Wait a second. No, this is not looking good. This should be little y bar. This set is actually y bar. Yeah. This whole set I think was x bar. Yeah. Yeah. Okay. So we get this graph. This is, I will call it as usual G21. And let's draw the other contraction. So I'll keep this part as it is. Y bar. This is y bar. And I will shrink all of this into single vertex. So this was basically in the original graph the complement of y. So I'll call it little y. And let me call this G22. Right? Do you all agree that G21 is exactly H12? Right? Let's see. This graph is the same as this graph. Yeah? And what is this fellow? Oh, that is this fellow. Is that correct? Yeah? This fellow is exactly the same as this fellow. Yeah? We didn't even argue this time that this is a tight cut or not. I mean, it is tight or not, I'm not sure. It is a separating cut for sure because we got two graphs that we already knew were matching covered in the past. Right? So therefore, we have already observed that this is a separating cut in a strange way, not the best way to observe it, but well, it works. Right? Okay, so therefore, these two are precisely, instead of, this is exactly B of G1, so let me just replace H12 by G21 and H2 by G22. These are exactly the same graphs as before. And now we need to somehow observe that this is related to this. Well, it should be. We came from G2 to these two graphs. So by induction, we know that the number of bricks in G2 is less than equal to the number of bricks in this plus this. Will that be enough for us? If we just prove that number of bricks in G2 is less than equal to Number of bricks here plus number of bricks here. No, right? That's not good enough. That's not good enough. What we want is equality. I basically want to replace this by this. So if they were equal, then I could do it. Okay, so let's think about that. Is this, we know it is a separating cut because we got matching chord graphs. They were matching chord in the past, so they continue to be. Is it also a tight cut? Is this D a tight cut in G2? It was a tight cut in the original graph. If it is not a tight cut here, take a perfect matching that meets the cut in 3 or more edges. And now observe that you can extend it to a perfect matching in the original graph. Every perfect matching of a contraction can be extended to a perfect matching in the original graph. And that's a general statement in life. Right? So therefore I'll just extend it and I'll get a perfect matching here containing 3 or more edges from this cut, contradicting the fact that D is a tight cut. So in fact, D is a tight cut in G2. This implies that the number of bricks in G2 is precisely the number of bricks in G21 plus the number of bricks in G22. Well, that is exactly what we have here. So you combine this and you conclude that the number of bricks in G is indeed strictly less than the number of bricks in G1 plus the number of bricks in G2. So we are done in this case. Yeah. Convince yourself that we haven't fooled ourselves by the drawings. So we made a lot of drawings, but you have to convince yourself that the drawings are fine. They are not misleading us in any way. Right? Of course, you can write the entire proof without the drawings, which is what many people do, even in published papers. But well, I don't know about that. But at least if I'm going to explain this, I'm not going to just write notation. Just notation is not going to serve much purpose. So yeah, make sure you convince yourself that these graphs are indeed the same, these are indeed the same, these are indeed the same. Right? In fact, in Lucchesi-Murthy, they leave case 1 as an exercise. So I could have done that, but I actually wanted to cover it myself. So I robbed you of one of the exercises. Okay, any questions, concerns, all good? Okay, so we are done with this case, and now we need to deal with the crossing cuts case. Right? Okay? So one possibility is I erase all of this. Yeah, may I erase all of this? Yeah, okay. The other possibility is we just move the camera here. Shall we do that? Okay, then I don't have to erase too much right now at least. Eventually we'll have to erase. Thank you. You can pause. Okay, thank you. So we are now left with case 2, the more difficult case. C and D are crossing cuts. Okay. So let's make a drawing as usual. So graph G, I'll draw C horizontal. This is the cut C, this is X, this is X bar. This is the cut D, this is Y, this is Y bar. And as usual, we will adjust notation so that X intersection Y is odd. Therefore, this is about any two odd cuts, right? So therefore x intersection y bar is even, x bar intersection y bar is odd, and x bar intersection y is even. Yeah. So this of course looks very much like the uncrossing lemma. It is pretty much the uncrossing lemma. The only difference is one of them is a separating cut that is not tight, whereas the other one is tight. Let's also write down to remind ourselves. This is the tight cut, and this is the cut that is separating but not tight. Yeah. Okay, so the uncrossing lemma doesn't hold, at least the way we wrote it. It required both cuts to be tight. But maybe some of the conclusions we want still do hold in this case. So did anybody try this? Did anybody try checking what happens here? Yeah? Okay. Anybody else? I'll come around and talk to you. Okay. Okay, see if you can figure out what conclusions hold. Right, so in the uncrossing lemma, just to remind you, we proved that there are no edges from here to here. So that was one point we proved. The number of edges between x intersection y bar and x bar intersection y, this is empty, this set is empty. And we also concluded in that case that I and u are tight cuts. I partial of x intersection y and u partial of x bar intersection y bar are tight. So my question is, do any of these conclusions hold, or do weaker conclusions hold? Maybe the same conclusions don't hold, right, because the hypothesis is weaker. So can we say something weaker? Right, so think about these points, and if you have something to say, raise your hand and I'll come and talk to you. Once again, your friend is the characterization of separating cuts. Right? For every edge, there exists a perfect matching containing that edge that meets the cut in exactly one edge. So you should probably use that to observe things. Convince me of one of the things. So it could meet this one in two edges and this one in one. Okay, so you're taking okay. So you're taking the edge, cutting which edge? You're taking which edge first? Any edge. Then there's a perfect matching meeting this cut and exactly one edge. And your claim is that it will meet this cut also exactly one edge. Yeah. It meets C in exactly one edge. So now submit T and only one edge. So what possibility is 1 plus 1, but that is not possible. Yes. Okay. These edges?
First condition goes through, the second goes through for separating, but we don't know if it goes through for
Is this robust or separating? Separating but not tight. Ah, okay. So in this case, the partial of x intersection y will not be tight. But it is separating. Yeah, you're on the right track. And then you can make more progress. That helps.
So what I would like you all to do is first try to figure out the first condition. This actually is very useful. Once you figure this out, things become a lot easier. So can there be an edge going from the E1 quadrant to the other E1 quadrant? Can there be an edge like this? If there is an edge like this, there exists a perfect matching containing this edge that meets the cut C in exactly one edge. If there is an edge like this in the graph, then because C is a separating cut, there exists a perfect matching that contains E and meets the cut C in exactly one edge. But this cut is already in the cut, this edge is already in the cut C. So therefore it cannot use any other edges from this cut. But how many vertices are there in x intersection y? There's an odd number of vertices. Right? So somebody has to be matched outside. So either you will get one more edge in D. This edge is already in D also, right? This edge is in both C and D because it is crossing both the pink line and the blue line. So either you will get another edge in D, contradiction to the fact that D is a tight cut, or you'll get another edge in C. But we chose a perfect matching that meets C in only one edge. So these edges are not there. Once you prove that these edges are not there, then something very nice happens. Right, so this goes through. Okay, so forget uncrossing lemma. You will get this conclusion. Does everybody see this? Everybody sees why the first one is true? Yeah? Okay. Now there is something really nice. And writing equations is sometimes helpful. So, this is our cut I. And this is our cut U. For any set of edges, but you can think of it as a perfect matching if you like. For any set of edges, I claim that, let's say M is your set of edges. M intersection C plus M intersection D is equal to M intersection I plus M intersection U. Convince yourself that this is true for any set M. Therefore, M can also be a perfect matching. What are the types of edges that can contribute to the LHS or the RHS? There are 1, 2, 3, 4, and 5 types of edges. The 6th type does not exist. We just proved that. There are 5 types of edges that can contribute to the LHS and the RHS. Right? To contribute, you have to meet at least one of the cuts. So an edge which is completely in the quadrant has 0 contribution here and 0 contribution here. So the only thing I have to check is these 5 types of edges. Observe that each edge in these 5 types, this one for example, the top one, it meets the yellow and the pink. Yellow is being counted here, pink is being counted here. The left hand side is basically pink and blue. The left hand side is what? It's blue and pink. And the right hand side is yellow and orange. Observe that the top edge contributes 1 to yellow, 1 to pink. Yellow, pink. 1 to LHS, 1 to RHS. This edge contributes 1 to blue, 1 to orange. This edge contributes 1 to pink, 1 to orange. This type of edge contributes 1 to yellow and 1 to blue. And now let's look at the interesting type. It contributes to yellow and pink and blue and orange. 2 to LHS and 2 to RHS. The main thing we use is that these edges don't exist. Those are the problematic edges. They don't exist. Do you all agree? This statement is true for any subset of the edges, and therefore it is true for every perfect matching. I should probably say, in fact, any subset. Yeah, was that a correct statement? Good. But now we can prove easily that both of these are separating cuts using this equation. For every edge of the original graph, there exists a perfect matching that meets the cut C in exactly one edge. It will necessarily meet the cut D in exactly one edge because he is a tight cut. So therefore you have 1 here, 1 here. 1 plus 1 has to be equal to 1 plus 1. So you have 1 everywhere. So therefore for every edge you have a perfect matching that contains that edge, meets the cut I in one edge, meets the cut U also in one edge. Therefore I and U are separating cuts. This equation is the key to everything. Right? This immediately implies
I and U are separating cuts of G. Yeah? Good. And we know that the cut C in our situation is actually separating but not tight. Therefore, there is a perfect matching that meets the cut C in 3 or more edges. Is that correct? Yeah. So I will get 3 plus 1, 4. And therefore, one of these cannot be tight. One of these is not tight. Take a perfect matching that meets the cut C in 3 or more edges. So what is the LHS? 3 or more plus 1. That is 4 or more. That cannot be equal to 1 plus 1. Therefore, at least one of these two numbers will be 3 or more. Therefore, one of them is actually not tight. One of I and U is not tight. This is the key thing. If you believe this equation, everything else follows. I and U are separating cuts, and at least one of them is not tight. This is very useful because we are trying to prove a strict inequality. Somewhere we need a strict inequality. This is where it will come from. The not tight one. Right? Not tight gives us strict inequality by induction hypothesis. Yeah. Okay, take your time to absorb this, appreciate it.
We haven't proved that if C is not tight cut, then equality comes out. We just proved that tight implies equality.
Right. We are going to prove. Yes, that's what we are trying to prove. We want to prove that we have assumed that C is not tight, and we actually want to prove strict inequality. But if I get a smaller graph where I have a separating cut that is not tight, then my induction hypothesis has strict inequality. Right? So that is where this will be useful. Right? Not necessarily in this graph, but in some smaller graph. Yeah, that's a good point. Yeah, in this graph we cannot say anything because it is separating but not tight, so we can't say anything. Yeah. Okay, questions, concerns, everybody's okay with this? Yeah? Yeah? Okay. Fine. So we don't have tight, but we do have separating. Okay, so now the plan is to make drawings. Yeah, we'll make lots of drawings. So we'll draw the two C-contractions, we'll draw the two D-contractions, and as you can imagine, that won't be enough, we will draw more graphs. Right? Let me record the observation somewhere. I think this is fine. I and U are separating. And let me also make a third point. At least one of I and U. Actually, I want to make drawings here. Let me erase this. Okay, so what do we know? We know that the number of edges from x intersection y bar to x bar intersection y, this is 0. We know that I and U are separating cuts of G, and at least one of them
say I without loss of generality is not tight. Yeah, I'm writing G everywhere because eventually we'll have many more graphs, so it will be confusing. Yeah. Good. So let's make drawings. So we'll draw the C contractions, the D contractions to begin. So how do I want to draw the C contractions? For C contractions I have to shrink these things. Okay, so I will draw the C contractions at the top and at the bottom. So the top one will be, I'll keep this part as it is. This is my X, and I have a vertex, little x bar. Okay, this is my graph G1. Okay, now let's draw G2. So I'll keep the bottom part as it is. And the top part will become little x. My graph G2. And this is a set x bar. Yeah. Okay. And now let's draw H1 and H2. So I'll keep y as it is. And this is my little y bar. This is H1. And now I'll keep y bar as it is. And I'll draw little y. My graph H2. Yeah. So far so good. Okay. Now let's project the cuts to these graphs. So let's see. When I shrink this into single vertex, this yellow cut still remains a cut in this graph, right? X intersection y. So let me draw X intersection y. This is my X intersection y. This is no longer y, this is X bar intersection y. The cut has one shore odd and the other shore also odd, even plus 1. Yeah, this is the cut I in H1. Do you all agree? And in this graph, which cut should I draw? In H2, what should I draw?
X bar intersection y bar.
U. Yeah, I'll draw the cut U there. Okay. So this is my X bar intersection Y bar. The cut is U. And this is my set X intersection Y bar. Right? This is even. Plus 1 odd. This is odd. Yeah? Okay. What should I draw here? Here what have we done? We have shrunken X into a single vertex. So again I should draw U. Yeah. So let's draw U again. This is again X bar intersection Y bar. And this is odd, of course. This is X bar intersection Y. This is even. And let's also draw something here by symmetry. Right, so we'll draw we have shrunken the x bar part, so the I is still intact. This is my x intersection y. This is odd. This is the cut I, and this part is x intersection y bar, which is even. This is the cut U. So I survives in two of them, and U survives in two of them. Yeah. Okay. So we have drawn the two C contractions and the two D contractions. Okay, great. They are all matching code graphs because C and D are both separating cuts. Yeah, no problem. All of these are matching code graphs, and by induction, yeah, not sure. Let's see. We can say something at least. Can we at least say something? Can we relate B of G to any of these graphs? D is a tight cut, so therefore H1 and H2. Yeah, we know that B of G is equal to B of H1 plus B of H2 because it is a tight cut. Right? That's how tight cuts work. Good. So, since B is tight, B of G is equal to B of H1 plus B of H2. This is starting to look very similar to case 1, but it is not case 1. The goal is of course similar, exactly the same. We want to prove strict inequality. B of G is strictly less than B of G1 plus B of G2. Yeah, this is where we are trying to go, but we are still here. So we need some way to relate these two fellows to these two fellows. Yeah, that's where we are at. Okay, so maybe this is a good time to take a break and we complete the proof after the break, or maybe you finish the proof in the break itself. I take a break. Okay, you can pause it.